Hello everyone, we are William Orozco and Howard Cao. We are going to present the final project for the Digital Signal Processing course. We are part of the graduate program of Electrical and Computer Engineering at UC Davis. So first, let's go through the agenda. We will describe the project first, then we will go with an overview of the code. Next, we will explain the design of the system and the three main stages that are data preprocessing, feature extraction, clustering, and codebook. And finally, we will show the results. Let's begin with the overview of the project. We built a speaker recognition system. Its goal is to determine who is speaking based on two sets of data. The first phase is the training stage, where we extract the features and generate some codebooks, one for each speaker. And then we do the testing by calculating the distance and obtain the minimum distance, Euclidean distance from the features of the speaker in the test dataset to the codebooks that we generated. Now let's go through the overview of the code. We used MATLAB to program the system. We have three main scripts: CopyDSP1, CopyDSP1 noise, and CopyDSP1 notch. All of them load files, they plot, they perform training and testing with the datasets. We also have auxiliary methods to obtain the MEL filter bank, the MEL filter cepstrum coefficients, and to calculate the centroids using the LVG algorithm. Finally, the most important method is the norm audio that we will explain later. So now let's talk about the design of the system. The first stage is the data preprocessing. Here we crop quiet regions that have amplitudes below -10 decibels. We also center the signal around 0 and normalize the amplitude to be between -1 and +1. In this slide, we show the result of the normalization step for speaker 3 and 10. For speaker 10, we can see to the right that the original signal is a stereo recording, but in our project, we only considered monophonic audio. So what we did is to choose only one channel of the recording, and then we normalize the signal for the training stage. Now let's go through the feature extraction stage. First, we apply the short time Fourier transform to frames of the signal. The length of the frames was 256 samples with an overlap of 100 samples, and we also applied the Hamming window to minimize the spectral distortion. Then we applied the MEL frequency wrapping with a filter bank of size 20. We also dropped the first DCT coefficient because it doesn't contain relevant information of the features of the speaker. In this slide, we see the results of the spectrogram of the speaker number 3. To the left, to the top, we see the original signal spectrogram, and to the left, to the bottom, we see the same spectrogram but without the surrounding regions. The blue regions are the quietest, so we remove them with the normalization step of the preprocessing stage. To the right, we see the compressed spectrogram by applying the frequency wrapping with a filter bank of length 20. To the right, to the bottom, we highlight the index 15. We should notice that below index 15, the amplitudes of the signal have higher values, and above index 15, the amplitudes are lower. So then we consider only the indexes 2 to 15 for the training stage of the codebook. In this slide, we show the same results for the spectrogram and the frequency wrapping for speaker 10. We see the same pattern in the MFCC for speaker 10 as because the frequency content, the relevant frequency content is below index 15. We can see this in the graph to the right to the bottom. Then let's talk about clustering and code words.
Okay. Clustering and code words. Clustering is an important part in speech recognition. The clustering method that we are using is Lind, Buzo, Gray, which is known as LBG algorithm. I'm going to talk about how the algorithm works and why is it LBG algorithm. Okay. It is used to design codebook, and it is most widely used approach. The process of placing these output points is referred as codebook design, and it is based on k-means algorithm. It is guaranteed that the distortion from one iteration to the next one will not increase. So what we do is we get to pick M clusters, and we get to decide an error threshold epsilon value that represent the largest distance between the data points and the centroid in the cluster. We also get to decide the splitting parameter, which is related to the rule of the LBG algorithm. So how does the LBG algorithm works? Codebook, clusters, centroids are the definition that are used in LBG algorithm. We use MFCCs to generate a codebook for each speaker. We pick M clusters to generate in a codebook. Each cluster exists a centroid, and a centroid is a data point at the center of a cluster. And a centroid is also a featured codebook of a speaker. Okay, so this is an example of LBG algorithm. It starts from a first centroid, and then it split and classify each cluster by distance and refine the centroids. Compute the average distortion and see if it fulfills the requirements that we set. If the algorithm don't fulfill our requirements, it will go on until it fulfills them. And this is the result that we apply LBG algorithm to speaker 3 and speaker 10 for cluster equals to 8. We can see from the left, the speaker 3 has 8 centroids and also 8 clusters, but we can't see it on here. And also, and for speaker 10, we have 8 centroids also. This is the feature of speaker 3 and speaker 10, which is known as the codebook for them. And the next slide is for speaker 1 and 2. And this time we change the cluster into 32. We can see that the clusters match with some of the data points because there are not enough data points that they can be separated. Next, we are going to talk about the results.
For the results, we varied some parameters like the window size, the overlap, the size of the filter bank, the number of clusters, and the signal employed to train our codebooks. So in this slide, we see the results that we obtained by setting the size of the window to be 256 samples, the overlap to be 100 samples, the length of the filter bank to be 20, and 32 clusters. First, we employed the normalized signal. So to the left, we see for the training, the results of the training, the centroids and the features in the dimensions 3, and 5 for speaker 8. And to the right, we see how the centroids fit the features of the test dataset for speaker number 8. The sampling frequency for all the speakers was 12.5 kilohertz. In this slide, we see that we see the results of the training and test using the same parameters, except that now we are using the original signal. In other words, we are skipping the normalization step of the data preprocessing stage. We realize that the clusters now are closer to each other. So in this slide, we see for speaker 8, also the same indexes than before, MFCC number 3 and 5 from the training and test stages. Here we show the results of the minimum error of each speaker for the normalized signal to the left and the unnormalized signal to the right. We see that the codebook error is below 5%, and the accuracy is 100% in all the speakers. In other words, our system was able to recognize all the speakers. Now let's vary the parameters. So we played with the parameters, and here we show the results of a window size of 100 samples, an overlap of 30 samples, a filter bank of length 10, and only 2 clusters. To the left, we see the test result of the normalized signal for speaker number 4, and to the right, we see the same result, but for the original signal without the normalization stage. The most important thing to notice here is that the clusters get closer when we skip the normalization stage. So here we see the accuracy of our system using the unnormalized signal. 6 out of 8 speakers were recognized when we use the unnormalized signal. However, when we normalize signal with the previous parameters, we achieved an accuracy of 100% for all the speakers in the system. So in other words, it means that the normalization step is very important to separate the clusters and to identify the unique features of each speaker. Now let's add some noise to the experiments.
For adding the noise, we use the function randomn in MATLAB to generate the noise to the signals. The randomn function generates pseudo-random numbers whose elements are normally distributed with mean 0 and variance 1, which is also known as a function to generate Gaussian distributed variables. We added 4 different variants of noise, which is 0.001, 0.0035, 0.006, and 0.013. Corresponds to the signal to noise ratio, SNR, 25 decibel, 15 decibel, 10 decibel, and 5 decibel, respectively. We can see that when the noise gets larger, the SNR drops. The best SNR that our system can tolerate is around 10 decibel for the added noise. When it goes to 5 decibel, our system starts to lose accuracy. It is because that the noise interfered with the signal and corrupted the message. As a result, most of the features of the signals are affected. This is an example of the signals of speaker 4 and speaker 6 with and without noise added. The figure is speaker 4 and 6 with a variance of 0.013, SNR 5 decibel, of course, which is a point that they lose accuracy from recognition. The next one is the speaker 6, that is also a variance of 0.013, and it also loses accuracy from our system recognition. Now let's remove some frequencies by notch filtering. We applied notch filtering on the training signal to generate different testing signals. For speaker 4, we set the notch filter centered at 1000 Hz with a bandwidth 400 Hz. The frequency response shows us which part it is going to filter out. We can see the result from the spectrogram that the filter does not change a lot with the loss of the high frequency. By contrast, in the next slide, we set the notch filter center at 500 Hz with a bandwidth 500 Hz. We can see from the frequency response from speaker 2 and speaker 6 that the relevant frequency content was removed. In addition, we can see a huge valley in the spectrogram of speaker 2 and speaker 6. We can also see the result from the next slide. And we can conclude that the spectrum of the speaker are concentrated at lower frequencies. This is why the accuracy of the system was reduced. Thank you.